Hello and welcome everyone to the second video in the operational amplifiers. Today we'll talk about the inverting and non-inverting operational amplifier. So if we have an input through the positive terminal or the input will be through the negative terminal, there will be two different aspects for this operational amplifier. We'll discuss this later in this video. So let's start. First, from the first video in this one, let's review all of these things very shortly. So we have the ideal op-amp connected through feedback between the output terminal and one of the input terminals, the V minus or the V plus. The two main aspects of this ideal op-amp, the V plus equal to V minus, so any voltage here at the V plus will be transferred to V minus with the same value exactly, or vice versa. Regarding the current, we have the input currents through these input terminals will be equal to 0, as Rn here between those terminals inside this model assumed to be infinite, so there is no current will go through this input terminals of the operational amplifier. Regarding the output terminal, don't forget, the output terminal there is voltage and also there is some current I/O. This current generally is not equal to 0. So, an illustrative example about this ideal operational amplifier. Let's assume here we connecting the positive terminal with some input voltage Vn. This is our source. And the V minus is connected to some resistance R1 to the ground. And from the same point it's connected to VO through a feedback resistance called R2. First, it's required here in this problem or in this example to find the ratio between V out over Vn, which is called the voltage gain of this operational amplifier. So to start solving any kind of operational amplifier problems, if it's ideal, so we have the first assumption. V plus has to be equal V minus, so both terminals should have the same voltage. V plus already known here, it's equal Vn, and V minus should have the same value, so Vn will be transferred here at the same terminal at V minus. So right now we have the other equation regarding the current. The current will go through this branch in red line will be 0, and from the other side here also, if there's this Vn connected to anything else, the current will flows through this branch will also equal to 0. So to get some relation through this VO and Vn, we have only the KCL equation along this branch around this node, which is the V minus. We can solve this in two different ways. Both are simple. So we can get VO connected to R2, connected to R1, then to the ground, and take this off outside the problem, and then applying the voltage divider, V minus across this resistance R1 will be VO, which is the total voltage across the series resistances, and then multiplied by R1 over the summation of both resistances. So V minus finally will be VO multiplied R1 over R1 plus R2. Make sure that this point is ground. If it's not ground, this voltage divider can be applied simply by this way. It should take care about the voltage difference between all points. The other way around, you can assume there's some current. This current is 0, so this branch has no benefits, and then the current goes through from V minus to the ground will be the same current going from VO to V minus. What about this IO? Actually, there is some current IO here, and also if VO is connected to the load from the right side, also there will be a current. So this node here at the output terminal, it's not recommended to use your KCL equation here. Just use KCL equation at the beginning, at the input terminals, positive or negative, it depends where is the current, where is the resistance are connected. So here you can assume V minus minus ground minus 0 over R1 will be the same to VO minus V minus over R2, which will give you the same relation at the end between V minus and VO. Again, substitute this one here in our only equation. So here Vn instead of V plus, V minus will be VO multiplied R1 over R1 plus R2, and simply this is your relation. So VO over Vn will be R1 plus R2 over R1, which could be simplified as 1 plus R2 over R1. R2 over R1 is a ratio between two resistances, so it's a positive number. Added to a positive number, so the total voltage gain, which is the ratio between the output voltage and the input voltage, will be a positive ratio. So this one called right now, it's non-inverting operational amplifier. Let's go second. In our second example here, we have an ideal operational amplifier again, and this ideal operational amplifier, the positive terminal connected to a ground, the minus terminal connected to R1 connected to the input voltage or the source, and then there is some also feedback between the minus terminal till the output terminal through resistance R2. Again, we have only just one equation, V plus equal V minus. V plus right now here is a real ground, so V minus will have a zero voltage. Take care, this V minus here, it's not a real ground, it's not a physical ground connected to the circuit. It's nothing but a point with zero voltage transferred through these properties of the operational amplifier, so this point is called a virtual ground. If you want to get some relation between this Vn and Vo, again, you don't have nothing except the KCL around this point. So here we have Vn minus this ground over R1 will be the current between this ground 0 minus Vo over R2. Again, we can here use this Vn, you can take this off again like the same previous example. Vn minus V minus over R1, V minus is 0, plus the other current, V naught minus V minus, which is 0 over R2, will be equal to 0. And then we'll get the very simple equation, Vn over R1 plus Vo over R2 equal to 0. This means the voltage gain Vo over Vn will be equal minus R2 over R1. Again, a ratio between two resistances, it's a positive number. This positive number multiplied by a negative sign, so it will be a negative number at the end, and this is called an inverting amplifier. So this is our second example. To wrap this off, here, if we have an ideal operational amplifier, this ideal operational amplifier, we have the input as in example 1 connected to the positive terminal. It will be called a non-inverting input or non-inverting operational amplifier. If you have your input through the minus sign of this input terminals, it will be an inverting input. It means the voltage gain at the end will be the relation between Vo and Vn through this minus terminal. It will give you a negative relation, which is inverting operational amplifier or inverting amplifier. So this happened in example 2 as we saw before, and this happened in example 1. Now let's go through some special cases in this operational amplifier. If we have non-ideality terms, so in case of not infinite gain, but a finite gain. So A it's not equal to infinite anymore, and then Vn not equal to 0 anymore. It means V plus and V minus are not equal as well. And the basic relation of any operational amplifier as a special case of a differential amplifier, the relation between V output and the V input, which is the difference between the input voltage at both terminals, it's VO equal the gain A, which now is a finite number, multiplied by this Vn. We still assume Rn equal to infinite, so infinite input resistance, and R output, Ro equal to 0, it means 0 output resistance. So again, VO will be A times Vn, and Vn still the V plus minus V minus. Let's go through some examples. So here we can consider this one. Go through the beginning. So here we have this example here right now. It's non-ideal op amp. The gain is not infinite. And we also required to get the relationship between the VO and Vn, like the closed loop operational amplifier gain or the operational amplifier gain between the output voltage and the input voltage. Here and here. The first relation, VO equal A times V plus minus V minus. This is inverting operational amplifier. So at the end we could expect the relation will have a negative sign. Again, V plus given and well known to be ground, 0. So V plus equal to 0. V minus here is not equal to 0, unfortunately. Not like the second example we solved before. So here we have to get some relationship between V minus and Vn in terms of Vn and VO. First, VO right now, it's nothing but minus A multiplied by V minus, and this is the first relation. Don't forget, we still have the same assumption valid for regarding the current. So IN, the input current through the positive terminal and the minus terminal, is still 0, as we still have the infinite input resistance. So here we can put this figure of the resistance taken off the op amp. We have Vn from this side, we have V out from the other side, and we have R1 and R2, and between of them V minus, which is not ground right now. To try to solve this relation, just using the KCL, still both input currents will be equal to the output current, which is 0. So Vn minus V minus over R1 plus VO minus V minus over R2 will be equal 0. And then move to the second part. Here, Vn over R1 minus V minus over R1 plus V out over R2 minus V minus over R2 will be 0. We have already relation between VO and V minus. So if we can get V minus as a function in VO and Vn, we can substitute with this relationship in the first equation, and then we'll have the final relation between VO and Vn. So here we'll take V minus common between this term and this term, the second and fourth terms will be V minus multiplied 1 over R1 plus 1 over R2 equal Vn over R1 plus VO over R2. And then this relation by substitution of the second equation in the first equation, VO equal minus A times V minus. We'll go through this equation. So right now it will be minus A multiplied Vn over R1 plus V naught over R2 divided 1 over R1 plus 1 over R2. To simplify this result, just multiply R1 and multiply by R1, R2, both numerator and denominator, and then we'll get the relation VO equal minus A times Vn multiplied by R2 plus VO R1 divided R2 plus R1. Let's continue here. So VO will be multiplied by this denominator. So here, VO multiplied R2, VO multiplied by R1 equal minus A times Vn R2 minus A multiplied VO R1. Take VO all terms in one side and Vn on the other side. And then just divide VO over Vn will give you this relation minus A multiplied R2 over R1 plus R2 plus A times R2. This maybe it seems somehow complicated relationship between VO and Vn. Let's consider A again is infinite, which is the ideal op-amp. If we substitute here with A equal to infinite, taking like the limit, or even do something much easier, divide by A in the numerator and denominator. This will be minus R2. This will be R1 plus R2 over A, and this term will be R1. So if we substitute with A equal to infinite, this term will be 0, and just will be left with minus R2 over R1. So if A equal to infinite, VO over Vn again will be minus R2 over R1, which already we got this solution at the second example in our video today. The second case we can consider as also some specific definition of this operational amplifier. It's called the saturation. What we mean by saturation, we didn't mention anything till now about the sources connected to this operational amplifier. So if we have any voltage source connected to this operational amplifier, it implicitly means that VO with any kind of amplification factor we will expect, this output voltage can't exceed the maximum of this V source or can't go below the minus voltage source. So right here, there is one main condition to take into account, that VO can't be greater than VCC, or VO can't be less than VEE. So what happens if this VO greater than this value, or VO is less than the smallest value of the negative voltage, or even if this one is the ground, for example? What happens? Let's assume here a signal Vn to use for this inverting amplifier. We have some values here for the resistance given, this R1 10K, R2 equal 100K, and VCC and VE given plus and minus 15 volt. From the example 2, we got the voltage gain of this operational amplifier equal to VO over Vn equal minus R2 over R1. If we substitute with the values already here in our example here, so it will be minus 100 over 10 will give you minus 10. So we have an amplification factor VO over Vn. The gain here is minus 10. It means if we have input voltage with 1 volt, the output voltage will be minus 10 volt. If you have Vn equal minus 1 volt, VO, the output voltage, will be 10 volt. So what happens if we have input voltage right now minus 2 volt? The output voltage from the mathematical expression should be 20 volt. But this is feasible? Do we expect that we can get some voltage more than the power supplies to the circuit? For sure, no. If you have any power supply for any circuit, so the maximum you can expect from your circuit, this is even something theoretically, approximately it will be less than this value, but theoretically, the maximum it will be allowed to get from your circuit, it's the same as your maximum voltage source in your circuit, the design circuit. So here VCC is 15 volt, VE is minus 15 volt, so VO will be some value between minus 15 and plus 15. So what about this 20 volt? This 20 volt, it means there is some saturation for the circuit. So no output voltage will be more than 15 volt. So it means from a very symbolic graph, if we have a relation between Vn and Vo, we will have a straight line. This is operation of the operational amplifier. It has some scalar multiplication with the input. So you have, this is the line, represent the slope of this gain, or represents the gain actually. And this gain have some value here, some angle here. This angle more than 90, as the slope is minus. So if we have a voltage 1.5 volt at Vn, the output volt will be minus 10 multiplied by this value, which will be minus 15 volt. More than this 1.5, something like this 2 volt we mentioned earlier. So 2 volt multiplied by minus 10 will be minus 20. But actually, nothing will be more than this VEE. So just it will be stop here at minus 15. So the value of the output voltage you will expect if you have any input voltage more than 1.5 volt, all the output voltage will be minus 15 volt. What happened on the other side if you have your input voltage negative since the beginning? So again, if you have minus 1.5 volt, the output volt is the relation minus 10 multiplied by this value. It will be plus 15 volt. And this is your maximum volt VCC. Any other values greater than the absolute value of this 1.5, like 2, 2.5, but in minus with minus sign. So for example, minus 2 volt, it should give you from the relation 20 volt. But this couldn't happen. So what actually happens, it will saturate the signal. The signal will be just 15 volt, nothing more than 15 volt. And this is called the case of the saturation of the operational amplifier. Here is the linear operation, and here is the saturation. To make sure while you are designing any circuit in the future, just make sure you're still operating during this linear operational stream of this op-amp. So again, here if we have Vn equal 2 volt, V out will be minus 15 volt, not minus 20. If Vnf equal minus 2 volt, Vo will be just 15 volt and not 20. This is called, again, this is the saturation. Okay, what happened if we have an AC source? What happened before? We just have a DC source. So what happened if we have our source as AC signal, like this sine wave? If you have 1 volt sine signal, so this sinusoidal signal between peak to peak, it's 2 volt. So it between minus 1 volt to plus 1 volt. This is your input signal. The output signal will be minus 10 multiplied by this one. Minus 10, it means it will be flipped. This positive will be negative. This negative will be positive. Again, with positive will be negative. And some scalar multiplication here. It will be amplified 10 times. So this 1 volt will be 10 volt. And this minus 1 volt, it will be minus 10 volt. Again, this is your output signal. Can we consider any saturation in this case? No. Why? There is no output voltage more than 15 or less than minus 15. So the output signal here is still operating inside the linear region of the operational amplifier. So let's assume something else. If we have Vn equals 3 volt and we have V out to be computed here, so between peak to peak it's 6 volt, so between minus 3 and 3, V out should be expected to be this number is multiplied by minus 10. So again, it will be flipped, the positive negative, and the negative will be positive. And 3 will give you minus 30, minus 3 will give you plus 30. But again, the voltage source connected to this operational amplifier just between minus 15 and 15. So just we can draw a straight line, this dotted blue line here at 15 minus 15. And this will clip the output voltage. It means if your output voltage, anything before this minus 15, it will be the same one as this black line. If it's something more than minus 15, like minus 15.1, minus 20, minus 25, minus 30, all these values just will give you output voltage of minus 15 volt. Again, if you have output voltage minus 14, minus 3, 3, 12, 15, it's okay. You will get the same values. If you get output voltage 18, 20, 25, 29, 30, all these values at the output just will see just 15 volt. And this is called a clipping circuit. So the circuit here will clip the output signal if we have an AC signal. Also, this is one application of the saturation. In the DC, we can call it saturation, or the operational amplifier work in the saturation region. In the AC signal, we can call the AC signal at the output have some operation happen to it. And this is what we mean by the clipping right now. By this clipping, we came to the end of our video today. And thanks for your attention and thanks for your time.